So we've examined binary in a pretty good amount of detail. We've even visualized binary sequences as yellow and black boxes to represent switches, either on or off, and even as candles that are lit or not lit. But have you ever thought about what binary might sound like? Well, in this lesson you'll learn about how a couple of guys from back in the days of the telegraph helped us to figure out a couple of really great ways to encode and transmit text and other things into a binary format. So you've had the opportunity to look at how both numbers and text can be represented with binary. So now we're going to look at what actually goes on behind the scenes when we encode or digitize data. Think back on when we talked about binary codes being equivalent to certain keys on the keyboard, or the ASCII, or even the Unicode set. Remember, there are lots of different possibilities for combinations, but one problem, if you've just got this stream, think of the last paper that you had to write. How many characters are encoded in that paper when you save it and try to submit it to your teacher? Just character after character after character. We've got all these streams of characters. How does the computer know where one letter or one word ends and another begins, right? So that is a big concern, is finding out where one symbol ends and the other one starts. All right, and just as a reminder also, I want to refresh your memory in terms of digitization on what that looks like in terms of, remember our 7-segment 8, right? So we've digitized the number 8. In other words, we've created it out of segments that can be either on or off. And then I could go in and I could turn off some of those, and now I'm left with a 3, right? So that's kind of another comparison for talking about digitizing data. But we are going to focus on actually encoding data into binary. All right, because it's such a problem, needing to know where one symbol ends and another begins, there are two common types of encoding schemes. We've got variable width encoding, which hopefully that word variable kind of leads you to the idea that it can change, whereas fixed width encoding would not change, right? The width of the character would not change. And so let's look at both of those in detail. Variable width encoding. This kind of seems more natural. Like our words. I could, a real simple sentence, something like, the cat was red. I'm pretty proud of myself. I just literally came up with that off the top of my head, and it illustrates my point perfectly. If you noticed, every single word in that sentence has 3 letters. Right? So if this were the norm, if every one of our words had 3 letters, it would be really easy to know that, okay, well, then you just put a space after every 3rd letter. Yep, put a space there. Yep, put a space there. Yep, put a space there. Yep, I'll put another space there. And then there'll be another 3 letters and another space, right? However, we know that that is not the case, right? Our English words don't all have 3 letters. Most of them have many more. All right, but it seems more natural to us that we would allow for however long it is, then we just put a space and that tells us. All right, but using codes of different lengths allows us a different number of bits. Like if it's a small word, then we can use a few number of bits, whereas if it's a larger word, then we can use more bits if needed, right? So some would require just a few and some would require many more. So every symbol would get a different number of bits according to how many it needed, all right? And that is actually used. So some forms of Unicode, because Unicode has both 8 and 16 and 32-bit representations for all of the characters, that is actually used. And a common form of compression, called the Huffman coding, does actually compress characters into sequences of variable widths in order to save space. So here's an example of variable width encoding. So Morse code, which surely you've heard about, everyone is familiar with SOS, was really one of the first digital codes. And in the code, letters are represented by combinations of long and short signals. So you can see over here, this is what was known as the telegraph key. And so you would make contact. So you would push this little lever down to make contact down here, and it would actually create a circuit, right, that would send a signal. And the length of time that you hold this down is the length of the signal. So of course you can hold it down for a long time, which is usually indicated by a longer dash, or for a short time, which is the short dash, right? So the code uses variable length encoding. Morse code uses variable length encoding because each symbol is represented by a sequence of these values, these longs and shorts. And the sequences for alphabetic characters, so for the letters, varies from 1 to 4 dots or dashes. All right, and typically the telegraph operator would pause between each symbol, and that's how they would know that one symbol was done and they were waiting for the next signal. So if you kind of look through here, notice that, for example, the letter Y, the letter Z, the letter C, the letter J, they seem to have much longer sequences than something like right here, the letter E, right, or the letter T, or even over here, the letter S. Those seem to be very short sequences, whereas these lesser used characters have a longer sequence. And that was done intentionally because we don't want our telegraph operator to get carpal tunnel syndrome. So, we want to make sure that if there's a letter that's used all the time, very, very frequently, that they don't have to make as many keystrokes to represent that letter. Yeah, and for example, the letter Q over here, that's got a pretty long sequence compared to the letter I right here and the letter R right here, which are more commonly used letters. All right, so that was done intentionally, and that is a perfect example of variable width encoding. All right, so the question is, how do you know where one character ends and the next begins? Okay, so with Morse code, we said that the telegraph operator would actually pause, take a longer pause, longer than any pause between dashes and dots, to show where one character ended. Here's an example. If you have ever had to work with a file, something along the lines of something.csv, you may, in your programming experience over the next few years, you might end up working with files like this as lists. But this is a comma separated value table. Okay, so this is like a spreadsheet, like an Excel spreadsheet or something like that. But when it is saved, when it's encoded, instead of having all of these lines and grid lines and column width and row height and formatting and all this kind of stuff, all it does is it pulls out the values on the table and separates them by a comma, right? And so that's an example of a delimiter. Okay, in that case, the comma is the delimiter. There has to be some way, when you're encoding something with this format, there has to be some way to show where one starts and where the next one begins, right? So think about the case of changing a really large Excel spreadsheet into a CSV file, to a comma separated value file. In addition to all of the numbers or characters or strings or whatever that are in the table, now you're adding commas to separate every one. And so that's good. Commas are very easy to pull out. You can easily transfer that file into another format, but the problem is you're adding size to the file beyond what the list contained. So in Morse code, the delimiter was the pause. That could lead to problems. For example, if you had to delimit Morse code, the difference between EE, which are two short pulses, right, short, and I, which is the long, is lost. You can't tell the difference between pausing between the two E's and the letter I, right? So you would always look for the shortest sequence that doesn't happen to appear with any of the letters. Like I could go to Morse code and say, all right, what combination of dots and dashes never appears in any of these? I'll use that as my delimiter. That probably would be a good delimiter choice. And again, in the case of a data table, obviously you would want a comma-separated value delimiter. All right, but with fixed width encoding, Now we have a little bit more predictable way to encode a character set, all right, for representation. So with this one, we're allocating a specific number of bits, all right? So if we're talking about ASCII, we're specifically allocating 7 bits. And in the extended ASCII table, we're specifically allowing 8 bits for encoding, all right? And every letter, even the ones that are shorter, like, so I don't have all these memorized, so don't think this is anything great, but I do know that space is 32 right here. So a shorter one, like the space, which is encoded as a 32, has exactly the same number of bits as the lowercase letter z, which is pretty high up on our table, right? Almost one of the bigger values in the ASCII table. All right, so they both have the same number of bits that represent them. All right, and this is how most modern encodings are done. It's done in a fixed width format. All right, so here's an example, and this actually looks very similar to what we looked at for the Morse code. However, this was code that was developed by somebody who recognized the problem with Morse code. All right, and this man's name was Emile Baudot, and he did this in the late 1800s, 1870, and he decided that he would use crosses and dots to encode 2 to the 5th, or how many characters? 2 to the 5th? Yep, 32. All right, and this code has a fixed length. All right, so when you're looking at this table, each symbol is represented by a sequence of 2 values, and the sequences for alphabetic characters are represented by exactly 5 on or off pulses. Okay, so now you look up here and you're like, well, I don't see 5, but there are 5. It's just that where are the empty ones? Okay, so here's the letter A. We've got 2 to start off with, which means that there are actually 3 offs, right? Because there are 5 letters. Okay, but for B, that's different. So the first one is on, and then actually the next 2 are off, and the last 2 are on. Okay, so this is a fixed width. Everyone has 5 spaces, I guess you can call them. It's just a question of where the dot is. And characters can be streamed without pause here. So when our telegraph operator is going to town trying to send a message, they don't have to take the time for that pause, all right, which is important, especially if it's an important message about an emergency or something like that. All right, so this is the Baudot code, and this is one of our first examples of fixed width encoding. The benefits of this system, of knowing exactly how many characters make up every letter and knowing where one ends and another one begins, is obvious, and that's known as segmentation. So again, that telegraph operator didn't have to pause between every character and didn't have to do the 1 Mississippi, 2 Mississippi thing or something like that in between every character. Therefore, messages could be sent faster. Probably this is going to decrease the size of the message because you're not adding anything in. Like in the comma-separated value example, we're not adding a whole bunch of commas in between every single value, because the comma would have to get represented by some way as well. You're not adding anything into the file, so you are helping with the size. And then in terms of mapping, it is much easier to map button presses, right? Think of that little telegraph key, since the physical number of wires and circuits is fixed. It's just much better, again, much more predictable, easier to check for errors. For example, if you know that you're waiting for 5 bits for every letter, and you get a message that has 24 bits, that's a red flag right there. Something's wrong. Okay, so you'll know that there's an error because you didn't get the expected multiple of 5, right? So it makes things easier in terms of catching errors as well. All right, so here's a comparison. So here's 2 different ways of writing the date. In the top, we have 2 digits for the month, 2 digits for the date, unless we're in Europe. We're going to assume that this is February 5th and not the 2nd of May of 2018. All right, and you notice that I could put any date. The biggest month that we would ever have would be 12, right? 2 digits. Biggest month we would ever have would be 12. Biggest number we would ever have is 31, right? So it would still be a fixed number of bytes. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. This is going to be 10 digits. to show a date. Whereas this one, we don't know. It could be 10, but what if this was 12? Now, all of a sudden, instead of 1, 2, 3, 4, 5, 6, 7, instead of 8, this is 9. All right, what if this one changes? This one is back to 2, but this one is now 30, right? So this changes. So this is variable down here. It's a variable with a method of representing the date. So you can imagine that when you're filling out an online form, and whoever's going to receive that form needs to have everything standardized. They need to know where your date of birth is. They need to know where your first and last name begins and ends and all that kind of stuff. You can imagine that when they're accepting a date, they probably would rather have it in a fixed width format to make sure that there are no errors. So after completing this video, you're going to read the summary that's right below, and then move on to the post-lesson exercise, where you'll be making your own digitization or encoding method with playing cards. Get ready, card sharks.
Ready, set, go. When I say go, flip over your card and send the message to your partner at the other desk, okay? Ready, set, go! Yell out as soon as you have the message and then read me the message. You can hear the Morse code. Can you hear it going on?
Yes, I can.
Okay. Very exciting. Let's see who is faster.